We're going to get started. We're waiting on a few, but we just decided to start. So welcome to the Bayesian modeling for agricultural data. We are Francisco Palmero, Trevor Heffley, and myself, Josefina Alcaza. We're from the statistics department at K-State. And let me first ask you, how many of you have tried to fit a Bayesian model to your data? If you can raise your hand. Okay. Okay. So this is, you probably heard of Bayesian data in the last years because it's gained a lot of popularity. And the Bayesian theorem actually was introduced long ago in 1763. But it was very complicated to fit data to those types of models because when you don't get a very good analytical result that you can write with pencil and paper, today we use computational algorithms that help us to do that. But it was really hard to get that before the 1980s, 1990s. So that's why this is just taking off right now. And what Bayes' theorem basically does is that you can have a prior belief on something, on some process that occurs in nature, or on some hypotheses. And what we do is basically combine that prior knowledge with data, and we update that knowledge, and we get our updated knowledge about the process, the hypotheses, or whatever we're trying to investigate. And so I know this crowd is really into machine learning because we're at a precision ag conference, which is great. It's great for, I mean, it's really cool, and I've read a lot of papers that apply machine learning, and it's great for predictions, but in this workshop, we're going to focus mostly on Bayesian statistics that can actually help some problems that need more interpretation or that need quantification of uncertainty. And even with Bayesian statistics is especially good for solving small data problems. That is basically a lot of our agricultural experiments are present small data problems. And we can, by combining our prior beliefs or our prior knowledge on how the world works, combining that with the data from our experiments, we can actually help solve some small data issues. And so we looked at, we did a quick search in the literature and search for agricultural related papers and either big data or big data sets and words connected to that concept, machine learning and Bayesian statistics. And so machine learning took off really fast, especially related to situations where you have a lot of data and you want to have you have prediction objectives mostly, and that's great. But then Bayesian statistics is also taking off, and it's gonna get better and better computationally, which is gonna make our lives easier and happier. And so that's really something we have to start reading and thinking about in the coming years. So today we're going to talk about that in these 2 hours. And Trevor is going to tell you a little bit about how Bayesian models work, making a connection between least squares, which we all know, and going to applied Bayesian models. Francisco is going to tell about MCMC, that are the computational algorithms that actually enable us nowadays to fit these types of models to data. And I'm going to tell about some model diagnostics and things you got to check after you fit your model to data to actually know that it's working. Trevor? Yeah.
All right. Well, thank you for joining us here today, and I'm incredibly excited to share the world of Bayesian stats with you. And I was basically told I got 40 minutes to tell you everything I know about Bayesian stats. So that's going to be a bit of a challenge, but I think I kind of found a way into your brain through least squares regression to explain at least some of the major reasons I would consider using a Bayesian model. And then we'll kind of talk about some general tools that may help you in your research, okay? We'll do that, and then we'll have about a 10-minute break after this. So I kind of want to start off with like an introduction to linear models. And so you're in the Midwest of the United States, and that's basically like the breadbasket of linear models. Iowa State, Kansas State, Colorado State, those are like the big name universities for linear models. And you may have a background in linear models and heard of it before, but I'd like to kind of go over some stuff that I think is mostly review for you guys. So I kind of like to start off with like my own definition of like what is a model anyways, right? And so it's like, to me, I think of it as like a model airplane, right? This thing is a simplification of reality, okay? It doesn't have that many parts, right? Like if you built a model airplane that had as many parts as like a real airplane, it probably wouldn't be a model. Okay, and so we're looking for something that's simpler than the real process or the real thing that generated the data. Okay, and so we're free as scientists to construct that model however we want. Okay, just like if I gave you guys like some like glue and wood sticks and stuff and told you to build your own model airplane in this workshop, like you could do whatever you want. Okay, and in some ways, as long as we follow certain rules, okay, we can build any kind of statistical model we want. And I think what Bayes' theorem brings to that is it gives us an actual theorem or a rule, okay, that tells us basically what we can and cannot do, okay? And so I'm going to walk you through a situation where we start with just simple linear regression and we build it up into a fully Bayesian model that allows for probabilistic inference and the use of informative priors and stuff like that, okay? So when we start talking about a linear model is more than a straight line. So for example, you maybe have seen polynomial regression. That's also a linear model, okay? But I'd like to keep things very simple here. And so I think of linear models, like at least the introduction to it, as probably the simplest usable statistical model I know of, okay? And so I like to use these 3 data points. I like to put my line of best fit through it. Okay, and I actually like to write that thing out if I can find my markers. Okay, and so in this workshop here, like a lot of times I'll say like yi, and so yi we call our response variable. Okay, and that thing's just going to be equal to an intercept. Okay, so most of the times in our models we're going to put some type of intercept. Okay, and then a slope, and then a predictor variable. So xi would be our predictor variable, and then we're going to have a error term. Okay, and that error term, again, this should probably be mostly review, but that error term describes maybe the discrepancy between our data and our mathematical model. Okay, that mathematical model is just a simple line. Okay, so that's kind of like where I'd like to keep things pretty much for the entire class. And the reason I do that is despite wanting to use more sophisticated things, I'm still very convinced that this is the most widely used statistical method in all of the sciences and will be for the foreseeable future. Okay, let's see. I did stop for those 2 points there, but we kind of have this mathematical part, right, a line, and then what I'll say is kind of the statistical part is that error there, okay? And the visual for this is like, I think everyone's seen this, okay? Just a simple line of best fit, okay? Some key things that I like about it are that, I always joke, but maybe it's not a joke, but at least in the United States, I'd say probably about at least half of the people that graduated from high school, when you say intercept and slope, it actually causes an image in their head, right? And to me, that matches with the definition of a model. Like, it's so simple that like we actually see it in our head, okay? And so I'd like to kind of keep you there as we build this thing up, because we're going to add pieces to our model here, okay? Any questions about that? Okay, let's see. So once we have a model, okay, we have a lot of options for estimation and inference, okay? And so probably the 3 most popular options are minimizing a loss function. So how many people have heard of least squares? Like everyone? Okay, so least squares, that is an option that we could use to estimate our intercept and slope, Okay? We're kind of following this logic of like we're assuming some stuff, we're taking data, and we're going to put that together, and that's what estimation does. It allows us to learn about things that we don't know about, given some assumptions and some data. Okay? So the first approach we'll talk about is minimizing a loss function, and that is a great place to start. Okay? Then I want to move into basically like the vanilla ice cream version of estimation for statistics, which is maximum likelihood. Okay? So maximum likelihood would have been invented in the 1930s, so it's been around for, what, almost 100 years. And frankly, that's probably my favorite estimation technique. Okay? It's very automatic to apply, and it works very, very well in a lot of situations, and it affords us full statistical inference. Okay? And that'll be kind of a driving theme here about this idea of making statistical inference. Okay? And then finally, kind of the last one, I guess, that's getting a little more popular, but it's actually probably the oldest, okay, is finding a posterior distribution, okay? And finding a posterior distribution is the way of Bayesian statisticians saying fitting a model to data, okay? You might fit a model to data by least squares, but like, again, in Bayesian stats, we kind of find a posterior distribution, okay? And then the final thing, like, I want you to remember is that, like, each of these options require different assumptions, okay? And as we go from least squares all the way to Bayesian models, we're adding in more assumptions, okay? Josephina hit this topic a little bit, but there are situations where we're information deficient or data deficient, okay? Just because you have a huge data set doesn't mean it has a lot of information in it, okay? And similarly, you know, not all the times do we have large sample sizes, okay? And so there will be times we want to add in assumption, and making assumptions are not bad things, okay? And the classes I teach, I mean, I always remind students, but it's like prediction and inference, this thing we want, I think of it as like some kind of fruit punch, okay? And we can pour in. We literally have two things to pour in. We have data and we have assumptions, okay? And we can make prediction and inference with assumptions only, okay? But we can't make predictions and inference with just data only. Okay, you're always going to have to add in some assumptions. And this gives us a nice way to basically decide what level of assumptions we're okay with and how we would like to progress with that. Okay? And I'll always kind of remind you that when we get to Bayesian models, like those are the most assumption-laden models out there. Okay? They're going to have the most amount of things that we had to assume. Or the analogy I make with the model airplane is like it's the model airplane with the most amount of parts on it. Okay? And if we add more parts to our model airplane, it better do something special, okay? And so, again, I'll show you that, what I think it does that's special, but we should not be adding assumptions without getting something, okay? So I'd like to start with the loss function approach, okay? And I think this will be a review for a lot of people, and I'm going to zoom out here, okay? The loss function approach, like, at least when I think about it, is we're going to define a measure of discrepancy. So I think of just a distance, okay? Like, for example, I don't know how far the hotel is away from here, but it's probably like, what, 1.5 miles or something? So that's a measure of discrepancy, okay, at least in geographic space, okay? So we're just going to define some measure, okay, between the data and the mathematical model, okay? So again, this component, we're talking about some measure of distance between that mathematical model and the data, okay? And so the visual I like for this, okay, is our 3 data points again and our line of best fit, okay? And so the 2 measures of discrepancy I have here is the squared error loss function, okay, and then the absolute loss function, okay? At least when I teach my statistics classes, I always describe myself as an animal, okay? And as an animal, I think in absolute distances. Okay, so I tend to like this loss function. Like when I think about how far I am away from the hotel where the conference is at, it's like 1.5 miles, okay? Squared error loss, right, it squares that. So you can take your numbers and square them. It's a little more challenging for someone like me to think about, okay? The point is like you get to pick this loss function. It's not really picked for you, okay? And it's just an assumption behind the model that you're using, okay? And so that's basically how the loss function approach works is like, you know, we could put you here and you could spend the rest of your life moving these little sliders around and trying different slopes. So I'll give you an example is like we could increase the slope of this line, okay? And we can see that the squared error loss increased by a lot, okay? Similarly, the absolute loss increased by a lot, okay? And that's why we would call it a line of best fit is because it minimizes some measure of distance, okay? So if I go back here and move this to 1.04, okay, I can actually prove mathematically that these values, negative 0.37 for the intercept and 1.04 for the slope, they result in a sum of squares, okay, that is equal to 1.75. You can spend the rest of your life moving these around and you will not find better values, okay? And so that's the beauty of least squares estimation. It gives us final point estimates, single numbers, okay, that we can use, okay, to actually communicate something, right? Think about this. Like, I'm usually not doing data analysis on 3 data points, okay? If you had 3 data points, you can probably just show the data points. You don't need statistics, okay? But what if you had 300? Okay, like I've looked at data sets with 300 data points, and I'm not smart enough to make sense of them, okay? And I'm not smart enough to communicate what's going on in it. But if I can boil it down to an intercept and a slope, like I've gained something, okay? And so this is kind of the simplest model, if you will, that we could have, right? And the simplest estimation technique, okay? So I'd like to move into an agricultural example, okay? And if you did get the email from me, I think there's 4 or 5 people that joined the class late that did not get an email. I don't know when I sent it. Was it yesterday at 5 a.m. or something like that? Please contact me during the break and I'll get this for you. Okay, but our real data example comes from one of Francisco's papers, and you can download it right here, okay? And I know nothing about agriculture, so this is a statistician's attempt to tell you about ag, okay? So just be aware of that, okay? So apparently there's a plant called a field pea, and I Googled it, and it is a real plant, okay? And then apparently there's something that people care about called the partial imbalance, okay? And that's what's on the y-axis there. Okay? And then on the x-axis here, we have nitrogen derived from the atmosphere as a percentage. Okay? So at least I did take a class in botany. Okay? So at least in the class I took in botany, if you got like 100% of your nitrogen from the atmosphere, that means all of your nitrogen came from the atmosphere. Okay? Similarly, if you got 0%, you were getting it from somewhere else, like the soil. Okay? So, uh-oh. Okay. I guess I have an hour to talk. So anyways, it's a classic data set where we might use a line of best fit. Okay? But here's the issue, is like we're not really interested in the intercept or slope here. Okay? Like, in fact, we don't really care about the intercept and slope. Okay? What we care about is where our line of best fit would cross this golden line. Okay? And that's called the neutral balance point. Okay? It's basically where there's no net gain or net loss, okay? And so this is a classic problem, at least I see in agronomy, is like we're using a model to indirectly get at something we care about. And that thing we care about, I'm going to call a derived quantity, okay? The reason I'm calling it a derived quantity is that it is basically a function of our parameters, okay? Just like a line of best fit has a y-axis crossing that we call the intercept, we also could derive from our intercept and slope an x-axis crossing. Okay? And we're going to use the mathematical notation. We'll call it theta here. Okay. Let's see. One other thing that I'd like to point out is all of the code boxes here, if you'd like to follow along. Okay? If I was taking this workshop, I probably wouldn't follow along with this stuff. But some people like to follow along. It's like you can copy and paste the code here. Okay? And if you have program R, feel free to run it yourself. Similarly, after the workshop's done, at least talk Josephine and Francisco to hanging around for an extra hour. So we'll hang around for about an hour if you'd like to try out any of this stuff yourself. Okay? So I've designed it, like if you want to follow along, go ahead. Good. Okay, so what we're going to do is fit this linear model to our data. Okay, we're going to get the least squares estimates of beta naught and beta 1. Okay, so I'm going to use the squared error loss function, and I'm going to use that to estimate theta. Okay, and that theta, again, that's the thing we're really interested in for inference. Okay, we want to know at what levels of NDFA, okay, so what levels right here would that line of best fit cross the x-axis. Okay, and that's a typical problem in statistics. Like, we're not always worried about prediction. We're actually worried about inference a lot of times. And I talk about inference, I'm usually saying trying to learn about something that's fake or not real. And parameters, intercepts and slope, are fake. They're not real. They're concepts in our mind. Okay, I don't know what the agronomist would say here, if theta is fake or real. But I think of it as a parameter, and it's probably more of a concept than maybe a real thing. Okay. So let's fit that model to our data. Okay, and so this code down here, if you haven't done it before, I mean, you can do this in Excel. In no judgment if you're using Excel for data analysis. I do all my personal finance in it, okay? And I do lines of best fit, okay? And so again, you could fit your line of best fit in Excel using least squares, and I think that's a method we're all familiar with, okay? And then what I would do, okay, maybe just intuitively, is I would take my least squares estimates. As statisticians, we like to put hats on things once they get estimated, so I'm going to put hats on those, okay? And I will judge you if you ask me to review your paper and you don't have hats on it. Okay. So we're going to take those estimates, okay, and we're going to get our theta value. Okay, 58. Okay, and so like before I move any further, I'd like to just go to 58 and say like, does that seem believable? Like, okay, seems good. Okay, we'll get to an example where it's like, I don't know if it's believable or not. Okay, but like in this data set, it's fairly information rich. It's a very small data set, to be honest. Like there's not that many points. Okay, and 58 seems about as reasonable as I could imagine with my own eyes. Okay, so we're kind of done at this point, right? Like we've finished all we need to finish. We could plot things. Okay, so I'll show you a visual representation of this. Okay. And basically, if you were asking me, I'd say like we're kind of done with this problem, right? We just report that value, theta is equal to 58, and like we're done, okay? And the reason we're done is we started off with the least squares approach, and least squares only provides us single values, we'll call them point estimates, of these parameters, okay? Least squares also makes the fewest assumptions. I mean, you know, if we're truly honest here, we just assumed a line and then we just minimize the distance between the data points and the line, the distance squared. So it's really not that many assumptions, okay? Which I really like. Like again, if I don't have to make assumptions, I'm not going to, okay? What it's deficient in, okay, is what we would call statistical inference, okay? And so one thing I'll talk about here is uncertainty quantification, okay? So when I think of uncertainty quantification, I think like, is that value of theta really equal to 58? Right? Because it seems like I could move this green line like over here and it also works. And I could probably move it over here and it also works. Right? And so it's like, with a smaller data set like this, like we're not 100% certain of this value. Okay? Similarly, we might have two data sets and we might want to actually do a formal hypothesis test. For example, that theta from data set 1 is equal to theta from data set 2. And because there's reviewers of journals, they'd probably want a p-value. We're not going to get that with least squares. We're not going to get any statistical inference. Okay? And that's fine. You may not need it. Okay? So what we're about to head into is the next level up. Okay? The next level up is likelihood-based inference. So we're starting in like the 1930s at this point. Okay, and so likelihood-based inference, like it takes our linear model, okay, and probably everyone's aware of this assumption. Let me see where the eraser is. I'm going to get rid of theta hat for a second, okay, and we're going to add something to it. And so the analogy I have here is like we have a model airplane and we're putting a new piece on it, okay, and you know I don't want to add crap to my model airplane unless it's going to do something really cool. Right? So at this point, I add a piece and it should fly, right? Or something like that, right? So I kind of think of the airplane flying analogy is like statistical inference. If we're going to add this piece, I better be able to quantify uncertainty, calculate the statistics that I'm used to when I'm doing things like a t-test, okay, or an f-test or something like that, okay? So the assumption I'm going to make here, and this is a big one, is the errors are normally distributed with an expected value of 0 and a variance of sigma squared, okay? So I'm sure you've all heard of the normal distribution, okay? And so this is the piece we're adding to our model, okay? Just as a side note, if you're doing least squares, you did not make this assumption, okay? And so I would call this a full statistical model. The reason I call it that is it has a mathematical model and then it has a probability density function or probability mass function. Okay? So in statistics, we have thousands of these distributions. The normal's nothing special. There's literally thousands of distributions. We'll talk about maybe why we chose that and what other options might be good. But just like in math, you have thousands of equations. Okay? And so you put those things together and you get like a full statistical model. Okay? The beauty of that is like if you bring this over to the stats department with your statistical model and you say like, hey, how would I ever fit this thing to the data, right? Like pretty much everyone could come up with a way. And they'd use maximum likelihood. It's a very automatic approach, okay? And that's the beauty of it. Given a statistical model, I always say you can literally shut off your brain at that point and just follow maximum likelihood estimation, okay? Undergraduate statistics majors will learn how to do this by hand and on a computer, okay? So it's kind of the vanilla ice cream of statistical estimation, okay? I don't know how this plot's going to go over. I've used it for years, and students tell me they have to stare at it for hours, and then eventually they understand it. And I tell them, like, that's amazing, because I stared at it for like 6 years before I understood it. But this is a graphical depiction of what maximum likelihood estimation does, okay? And so I'll attempt to explain that, okay? And maybe it will resonate with you, maybe it won't. Okay, so as the name implies, we're maximizing a likelihood function. Okay, where does this likelihood function come from? Well, if you go ask any statistician, they'll say, well, you just told me. Here's your model. It's fully statistical. I can get the likelihood function from it. Okay, and so this is the mathematical formula of the likelihood function, and what it spits out is a likelihood value. Okay, probably almost everyone in this class has like seen or heard of a likelihood value before. Okay, it's kind of standard output in a lot of models. Okay, and we're just trying to maximize that. Okay, and what we have to make this number as big as possible is we have 3 knobs. We have an intercept, I guess you can see it all, a slope, and a variance. Okay, that variance is this piece. Okay, so you can just move these around the rest of your life. And that's basically what numerical methods do. They just move those around until you find the value that maximizes this. Okay? Visually what's happening is we have our line, okay? And at each point that we have a data point, we have a bell-shaped curve or a normal distribution whose mean or expected value is, expected values are like where that distribution would balance, okay? That's describing this situation, okay? And what the data points represent here is like how far they are away from that high point. Okay, so the high point would be right at the middle. It's like obviously no data point's going to fall right on that line, and so they fall a little away from there. And so we're trying to basically maximize these heights. Okay, these heights would be called the likelihood. Okay, so you can sit here all day and it's like, let's make the variance really small. So these are bell-shaped curves. You make the variance small, it's going to squish them in. Okay, which at first probably will look good, and then after a while it'll start to look real bad. And so let's see what that would look like if I make that small. It's like, ooh, this is a very unlikely point. Okay, it's out in the tail of the distribution now. Okay, and so clearly this is not the maximum likelihood estimate because this number almost doubled. I already talked about this a bit, but I was like, we did add assumptions to our model. Okay, and so if we're adding assumptions to our model, like we should get something. Okay. And what I would say here is like the beauty is we get full likelihood-based statistical inference, okay? And so if you talk to statisticians, they would know what full likelihood-based statistical inference is. You may not know, okay? But it's things that you're actually using, okay? So p-values, confidence intervals, prediction intervals, anything like that. Most of what you think of as far as statistical inference comes from likelihood-based inference, okay? Okay? So what I'd like to do now is like basically do the same thing as I did before, okay? But I want to find the maximum likelihood estimate of that theta hat, okay, using this, okay? So how are we going to do that? There's a million ways to do it, okay? I'm going to use some very old school software. So if you've done mixed models, potentially you have used the package NLME, okay? It was built probably when I was in elementary school, from what I can tell. Okay, so it's a very old package, widely used, okay? And within there, you have something called GLS function, okay, which just stands for the general linear model, okay? And you can specify the estimation approach. So how many people have heard of REML before? Okay, we at least got one. Okay, so if you do a lot of mixed models, you run into REML. It's like vanilla swirl ice cream or something. It's just slightly different than maximum likelihood. So a lot of these more complex models, you'll be able to choose which type of estimation procedure you get. And so I'm going to choose maximum likelihood. Okay? Maybe the most anticlimactic example here is like I go through my derived quantity calculations. So I take my beta hat, my intercept estimate, my slope estimate. Ooh, I should judge myself. What? Yes. I'm not very good at basic math, and that's true. Okay? And we end up with 58 again. Okay? So you're like, okay, Trevor, you just took us through this, and we got the same answer. Okay? And I kind of shrug my shoulders and go, yep, of course, right? And so there's probably an annoying result, okay, that's not very well celebrated and shouldn't be very well celebrated, but it turns out that the linear model, when you assume residuals or error terms that are normally distributed, okay, it gives you the same estimates as least squares. They're two different approaches, but they give you the same intercept and same slope. Okay? Nothing other than like a fluke. Okay? It's not really that important of a result. Okay? When we learn it in statistics, we're like, oh, wow. And then like in practice, you kind of go like, well, I would use least squares when I just want single point estimates and don't want to do statistics. Okay? You would use normally distributed errors when you want to do full likelihood based. Okay? So the fact that they give us the same point estimate, it's kind of like, okay, that doesn't mean too much. Okay? What I'm happy about here is that I can actually get things like confidence intervals and standard errors. Okay? So there's an approach called the delta method. The delta method is a really old school way of getting standard errors for derived quantities. So anytime you're interested in the function of parameters, so anytime it's like beta naught times something or beta 1 times something or any function of those parameters, that's what the delta method's for. Okay? You can get at standard errors. From those standard errors, you can construct confidence intervals. Okay? The type I construct here are wall-type confidence intervals. Okay? They have the classic, you'll recognize this, plus or minus 1.96. Okay? So these are 95% confidence intervals. Okay? And that's kind of the beauty is that's a 95% confidence interval for theta. So I'm starting to get statistical inference, right? I mean, think about this. Like, how many people have calculated the coefficient of determination, or R squared? Okay, why do you get away with publishing that as a single number without a confidence interval? Probably because you haven't heard of the delta method, which has been around for a couple hundred years. Okay? The delta method, if you wanted confidence intervals on R squared, like you can do it with the delta method. Okay? And so, again, once we're doing fully likelihood-based inference, we basically can get full statistical inference on anything that we're estimating that's a function of those parameters, including R squared. Okay? Any questions about that? Okay, so I like this. Like this at least makes me feel like I'm doing statistics at this point, right? So at least in my own practice, I would say, you know, without a lot of warnings, I'm never going to hand over a single number. Okay, and I teach students this in my class is like, I think kind of ethically moving forward, like the bare minimum to hand over as results is probably a point estimate and a lower and upper bound of that. And I think a confidence interval is a great way to do it. Some people would say like you can get away with two numbers, the point estimate and a standard error. And I say like, I don't really like standard errors. It's tough for me to think about what they look like. When I think of an interval, I go like, oh, it looks like this. Okay? And so what we have here, okay, is the vertical dark line. That's the 58 that we had. Okay, that is our best estimate. In fact, it's our maximum likelihood estimate. I mean, if you really force me to pick one single number for theta, okay, I would pick 58 because it's the maximum likelihood estimate. Okay? But what we can show here is the uncertainty in that through a 95% confidence interval. Okay? Any questions about that? So I think maybe up to this point, everything I won't say is review, okay? I think things like derived quantities, probably at least that language is new to you, and that's why we also have some handouts. So handouts full of definitions, okay? Probably the delta method you hadn't seen or heard before. You probably maybe guessed, you're like, wait, how do I get a confidence interval on this thing, or how do I quantify the uncertainty? Okay, but this is using pretty old school techniques that have been around, I mean, honestly, since 1930. Okay? Any questions about that? Okay. So now, I guess this is what everyone's here for, is the Bayesian approach. Okay. And so the Bayesian approach says add more stuff to your model, okay, and it should do cooler things, okay? And so I want to walk through this example with the Bayesian approach, okay? And so let me grab my eraser here. It's like I added this assumption, okay, which again is like adding a piece to your model airplane, and like nobody got mad at me, so that's good. Okay, so apparently you guys don't care about this assumption, okay? And so it's like I'm just going to keep adding assumptions, okay? And so the assumptions I'd like to add here are that beta naught is normally distributed with an expected value of 0 and a variance of 1 million, okay? And that beta 1 is normally distributed with a variance of 0 and, expected value of 0 and variance of 1 million, okay? So since you didn't question this, you're not going to question that. And we're good to move forward, right? Okay. And again, like knowing what you know now, you're like, okay, we should get something for this, okay? And so in Bayesian statistics, we like to call these things priors, okay? All a prior is a model for your parameters in your model. I know that's a little bit confusing, okay? But this is a statistical model, okay? And we typically, in Bayesian stats, we call these priors, but they are just models for our parameters, okay? If you've ever used, how many people have used random effects or mixed models? Okay, a lot more people. So when you choose between a fixed and random effect, you're choosing between a model, the fixed effect, that has no models for its parameters, okay, or the random effect, which has a model for its parameters, okay? Some people have actually called these random effects, okay? So we're adding that on here. And the beauty of adding this is like all of a sudden we can use Bayes' theorem. Okay, so Josephina mentioned it, but if you go back to 1763, okay, like Bayes' theorem was published, and it's like straight up it just tells you how to shut off your brain. Like any theorem, you can just go ahead and apply it, and it works. Okay, and it provides fully probabilistic inference. Okay, the only thing that I would say is a strike against it is I had to add a couple assumptions. And again, you're the first one to question me adding stuff to my model, right? And so it's like, so you used the term, you said, basically these added assumptions need to be based off the data. And I'd like to modify that and say like, no, I mean, we made all these assumptions and I didn't look at the data and I was fine with that. And people use the linear model all the time without looking at their data, right? And so it needs to be based off our expert opinion like any model. Just like you're building a model airplane, like that thing's gonna be built off your expert opinion. Okay, eventually we'll get to model diagnostics, which is checking models, right? And that's when we'd make the formal comparison with data, okay? But I would argue all these assumptions should be based off your expert opinion or the science behind it, okay? And so you're getting dead on about where we're headed next is like, this is a pretty vague assumption, right? This is just saying, hey, I think the intercept basically is somewhere around 0, but with a variance of 1 million. I mean, that's huge. It's basically saying it could be anything. Okay, so it's a very vague assumption. Okay, and we're going to get to a situation where we're not going to get away with such vague assumptions. Okay, and then we will use the science, okay, to help us revise our model. Okay, if you're further interested in that, it's like that link to the paper right here. That's all this paper is about, basically. Okay, it is like how do you take that knowledge and turn it into these type of assumptions to help you out. Okay, so again, I'm trying to show you like plain Jane Bayesian stats. Okay, not trying to do anything too fancy. Okay, and so as far as statistical inference, and this is one of the reasons we love it, is we can just use what's called Bayes' rule or Bayes' theorem. Okay, and like there's really not much to actually contribute here. Okay, it's very automatic, okay? And so I won't spend too much time talking about these here, but it's like you can just accept those are fixed in stone, okay? And that's how we're going to do statistical inference, okay? I think the only thing I'd like to add here is like before about 1990, okay, these integrals, okay, from calculus, right, were basically impossible to solve with pencil and paper. Okay, and in 1990 there was an algorithm called Markov chain Monte Carlo that was, it wasn't really introduced, it was popularized. It had been around since the 1950s-ish, okay? And we realized we could apply that algorithm to find the posterior distribution. Okay? So in 1990s, I don't remember what computers were like. They weren't, well, maybe they were more usable than today, like exactly today, but like maybe like before Friday, like Thursday, okay? And so again, like 1990s, you started to see people playing with this. And then by early 2000, as Josephina showed, like people are actually starting to use this at a pretty steady pace, okay? And so that's kind of the beauty of things here, okay? The other beauty is like we get fully probabilistic inference, okay? And what I mean by that is like when I talk about an intercept or a slope, our parameters, I no longer get a single value. I get a whole distribution of values, okay? And so it invokes that idea of probabilistic thinking, right? Meaning that the slope's not just one single number anymore, it's actually a probability distribution. Okay? Now we could summarize that probability distribution. I'll talk about ways to do that, but that's straight up Bayes' theorem, right? It gives us that. And as statisticians, like, I really don't want to hand over a single value of a slope. I'd rather just hand over the distribution to the people, okay? And they can summarize it however they want, okay? So how would you, I mean, literally, I'm asking you, this is the model fitting algorithm. Okay, someday I may have a very confusing app like I did for maximum likelihood to show you visually what's going on here. I have not figured that out, and I have not seen any other statisticians present something like that. Okay, so we don't have the same nice visual as like least squares or maximum likelihood here. Okay, what we have is basically conditional probabilities. Okay, how would we fit that model to data? Well, again, we'd probably use something like Markov chain Monte Carlo. And so what I have here is my own homebrew version of a Markov chain Monte Carlo algorithm, okay? And at least what I hope to impress upon you is like, it's not actually that hard to program those. Like Markov chain Monte Carlo is pretty darn easy, okay? And we do have a lot of citations through this book, but basically there's a textbook I wrote in my early 30s when I was burning my time. Okay, and it basically, on chapter 11, has this code here. Okay, so if you're interested in more, I'm not going to spend too much time on that. Okay, but we do cite these books. This is the companion book, which I did not write. Okay, for this one, that basically tells you how to write out your models. Okay, this one tells you how to fit them. Okay, but the reason we wrote that book is that we found that people were really searching for different types of software to fit Bayesian models, and like frankly, like it's a few lines of code. Okay, it's not maybe as complicated as you thought. And at least when I learned Bayesian stats, like we had to learn all this specialized programming languages and all this stuff, and that was really hard and time consuming. And I was like, oh, behind the hood, it's not doing that much. Okay, and so this may look like a lot of code to some of you, but it may not. Okay, and so I'm only using one R package. Okay, so that's kind of my first observation is like, it doesn't really use much. This basically allows me to sample from a multivariate normal distribution. Okay? The rest of the stuff that I'm showing you isn't much. It's really setting me up for success. In fact, it even says this function is not really required. Okay? And I want to show you the meat of what's going on here. So this is all preliminaries. Okay? But if I'm actually talking about the Markov chain Monte Carlo algorithm, let me zoom out. This is it. Okay? It's not particularly a lot of code. Okay, so if you go like, hey, I want to fit a Bayesian linear model, right? At least if you were like me, you'd probably go to Google, try to find an R package. Maybe you use SAS. Okay, SAS actually has some phenomenal tools for Markov chain Monte Carlo. Okay, but at the end of the day, like what's going on behind the scenes generally is not particularly that much code. Okay. Right, and so it's like, at least, you know, in my own class, I say like, okay, so not every school has a department of statistics, first of all, right? Like they're actually kind of rare, okay? So if you go back to your universities where you got your degrees, like dig in and see if they actually have a statistics department. And they might have a biostat department, but that's not statistics, okay? That's like statistics for human health, okay? And so like, first of all, I'd be like, who are you getting your advice from on this, okay? And so again, it's kind of like, I think within the stat world, our advice would be like, why do things like JAGs exist? They're really complicated tools to do something simple. They may not be aware of model fitting algorithms like MCMC. Okay, that may be kind of, you know, newer to them. And again, in statistics, I think, you know, 30 to 40 years when something becomes popularized in stats and we say like, this is cool, you should use it, it takes 30 or 40 years before it really gets out. Okay? So again, one of our motivations for writing the book were for practitioners, like biomathematicians, to understand that MCMC is like pretty simple. Okay? Okay, so that's our way we're going to fit the model. Again, you've mentioned JAGs. We'll talk about JAGs later. We'll talk about Stan. We'll talk about all these different software packages that attempt to automate this. Okay, you can fit it however you want. Okay, there's going to be all kinds of software out there that helps. Okay, and so using Markov chain Monte Carlo and my own homebrew version of the linear model, I can fit this thing right here. Okay, you'll probably have a lot of questions about this. The only ones I would really like to talk about right now are these right here. Okay, and these things are adding this assumption to the model. Okay, we'll talk about other things like burn-in and stuff like that when Francisco talks about Markov chain Monte Carlo. Okay. So what do I get? Like, we added crap to my model airplane, like we should get something, okay? And this is kind of like the result that statisticians love is like, we no longer get a single value for slopes and intercepts, we get posterior distributions, okay? So given our model, our assumptions over here and our data, we put those together, Bayes' theorem tells us how to put those together, and we get basically everything we know about these parameters. So at first I think this is overwhelming because you're like, great, you just took something very simple, a line of best fit, and you gave me thousands of slopes and intercepts, and like that seems like you made my life harder, okay? And I would agree, okay? Unless you're used to looking at distributions like statisticians are and recognizing their characteristics, it's probably not that useful, okay? So I would like to summarize these, okay? I'd like to summarize them with what we call expected values or the mean. Okay, I'd like to summarize it with the quantiles or any other metric that you find useful. Okay, and you're free to do that. Okay, you can summarize them however you think you need to for your application. But before we do that, and this is kind of another cool thing about Bayesian stats, is like we got to calculate theta. Okay, and we're going to calculate that by just taking the random values from here and using that formula for theta. Yeah, so it's basically a Monte Carlo style sampling algorithm. So you can take draws from a distribution, okay, and it's Markov because they're dependent draws now. One of the beauties of MCMC, we call this the invariance property, okay, but like the invariance property I think of as like you can just use your intuition. You just transform those variables using that formula we had, and we get the posterior distribution of theta. Okay, and as statisticians, we'd say like this is the most information we know about theta. Okay. It's the most information rich, okay? And again, personally, like maybe towards the end of my career, I'll just be able to hand this to scientists and be like, I am done, okay? It's yours, okay? But again, we may need to summarize it into single numbers, okay? Or uncertainty intervals like quantiles, okay? Let's see. So that's what I'm going to do next, okay? And so I calculated the expected value or the mean of that distribution. It's 58, so basically the same as we got before. Okay, and then I calculated the 95% credible intervals, which became out to 52 and 63, about the same as before. Okay, and our visual here, I'm very skeptical. There is no line of best fit anymore. There's many lines of best fit, so I didn't want to show those. Okay, but these are our quantiles of that posterior distribution. This shading down here represents that posterior distribution. Darker shading means more likely values. Okay. Basically, the results are the same. Would you agree? Not much difference? Numerically, they look about the same. Okay? And so, like, my first takeaway is like, well, we added crap to my model and it does nothing different. Sure, I get probabilistic inference, but maybe you don't value that so much. Okay? And this example, I would say, is like the information in the data is pretty strong. When information is rich in our data sets or our data sets are very large, it's like assumptions should matter less. And the fact that we get the same numerical results from our data set is really just a sign of the quality of the data set. Okay, the assumptions don't matter that much. Okay, so first of all, it's like, you know, don't be afraid of Bayesian stats because like it will give you the same answer if the data have a lot of good information in it. Similarly, if you need probabilistic inference, okay, and there may be cases you do need it, okay, specifically in prediction, okay, like forecasting, long-range forecasting, we may need probabilistic inference, okay? So what I'd like to do is move to an exercise that kind of demonstrates a completely different scenario, okay, and just walk through exactly what we just did, okay? So apparently there's a plant called the white lupine. It's real. I Googled it. It looks like a flower, okay? And what do you think about this data set? Lots of information. What should we do with it? There you go. So, I mean, I think this is a legitimate question in the sciences, and I work in our stat consulting lab here, in addition to being an associate professor, okay? And like a lot of data sets come in, and they're small, they're information deficient, okay? And the problem is they're asking an important question that needs to be answered, okay? And like, who knows? I don't, Francisco might know, but it's like, I don't know how many years it took to collect this data set. I mean, it probably took some time, okay? And it probably cost some money. Okay, and I think our options, again, like we could just throw the data set away, and that's called publication bias, right? And we know how that's working out, okay? Or we can move forward, okay? And I would prefer that we move forward. I'm really not a fan of throwing away data sets. So I'd like to move forward, okay, and show you the techniques that we just walked through, and we'll see a benefit of using Bayesian methods, okay? So if we use least squares, we're going to do the same thing as before. We get a theta of 93. The visual representation is this, okay? What do you think? We good to go? Everyone's good to publish this? So we're publishing a class paper when we're done with this. Like, you're putting your name on this, right? Okay, this seems wrong at this point. Like, I mean, 93, I don't have the problem with this being 93, okay? But it just feels wrong to even move forward. Like, I'm just not going to give someone 93 without at least showing them this plot and be like, that's where I got it from, okay? So we're kind of stuck there. Okay, so I'm going to say like least squares, like I'm not going to use that because frankly, I think there's a lot of uncertainty here and I need to communicate that, okay? You know, in class I get a lot of questions. People will say like, well, least squares is unreliable. And I would say like, no, it's not. It's just a line of best fit by least squares. It didn't change because this data set is information deficient. It's still least squares. It's a very reliable approach. The problem is we don't know this with much certainty. Okay, you can move this green line around quite a bit and like you probably feel about equally the same about those numerical values. Okay, so let's go through likelihood-based inference. Likelihood-based inference is where I would head because I want to quantify the uncertainty. I'd like to give you a 95% confidence interval. We're going to go through that, use the delta method like before, and we get values between 76 and 109. How many people are good with this? I'm not. Like, I look at that and I'm like, oh, we just made things worse. Like 109, okay, I did take one botany class, remember? And at least we learned that you can't have more than 100% of your nitrogen derived from the atmosphere. That's not cool. Okay? I mean, ad hoc, we could just move this line to 100. Okay? I don't really want to do that. Something's wrong with my model airplane. Like if I threw my model airplane and I thought it was going to fly and it just nosedived, I'd be like, okay, I probably need to go back and revise it. Okay? So I'm not good with this. Maybe this makes you feel better, but like I'm also not good with this. Right? Like, do you really believe that the partial imbalance or the theta is or like basically where these data points are at? I mean, we literally have no data points that are in the positive. Okay, so what I think is happening here is like this confidence interval is way too wide. Okay, in fact, I know it's too wide. Like, it can't be over 100. Okay. This comes back to your question. It's like you said, well, shouldn't you actually sit down and think about this? And I would say, yes, that is the whole point of modeling, is actually to slow us down and make us think. Okay? And so I'd like to go back to my model and think about the slope. Okay? I talked to a fair amount of agronomists, and they said they didn't know anything about the intercept. Okay? But they said, I know a lot about the slope. And I said, like, okay, would you be okay with the value being negative? Like going like this? And they're like, no. They're like, that would never happen. Okay, so I'm like, I guess I can exclude negative values. So I could go over here and just say like, the slope's never going to be negative. Okay, and really, if you sit down here, it's like we know a lot about slopes. Okay, and so this process is called expert elicitation. Okay, and you might work with an expert that's worked on this species and say like, okay, but if you were to take your best guess of the slope here, what is it? Okay, and so we came up with an assumption, okay, that this slope is equal to 2.5 as an expected value. So on average, we think it's 2.5. And I wouldn't say we're hugely uncertain about it, but we're going to set our variance here equal to 0.1. Okay? So we just changed our assumptions, okay, using expert knowledge. Okay? I didn't really add anything to my airplane, but I would say this is a much more restrictive assumption. Okay? And in Francisco's paper, he'll tell you about a much more elaborate way to come up with like really smart ideas of how to come up with these numbers. Okay? This one's more designed for the workshop to make it a little bit simpler. This would be the prior, right? So these are my assumptions. I'm going to combine them with the data, and I'm going to get that posterior. Okay? And I think this is reasonable. Like, I mean, again, like none of these species of plant like have a negative slope. Okay, like shouldn't we use that information? Like if we go to least squares and likelihood, like we don't get to use those assumptions. We don't get to have models for our parameters. Okay, and so here we're going to use that information. Okay, and we're going to go ahead and fit that model to the data. Here are our posteriors of our slopes and our intercepts. Okay, not particularly useful here, but I'd like to look at theta real quick. Okay, so theta there. How does it look? Well, it has a couple values over 100, but not too many. And again, in Francisco's paper, he actually talks about coming up with priors that will make this not happen. Okay, they're smarter distributions to use rather than the normal distribution. Most everyone's probably heard of the uniform distribution. That'd be a good one to use here. Okay, so here is our new posterior distribution under different assumptions. Okay, we can calculate its mean, expected value. Okay, the mean of this is 88. The 95% confident or credible intervals would be 82 to 95. Those seem reasonable. Okay, if I'm going to present my final results here, it's like that's it. Okay, and so we were able to take a very data deficient situation, add in what I would argue are realistic assumptions. Like, I mean, I'll argue with you all day about what the numerical values would be here, but like that slope has to be positive. Okay. And you would be shocked about how much that will reduce uncertainty by just having information that it should be positive and being able to put that in your assumptions. Yeah, so I would totally agree with you. And I would say, like, for workshop purposes, okay, I kept things simple. Okay, the algorithms to fit that when you change that are a little more nuanced, and I didn't want to have like piles of code there, right? But yeah, absolutely. Francisco in his paper talks about that. Something that would have a compact support, right? So that's all I have for the linear regression model. I think I would summarize with like, Bayesian models, they require more assumptions. Nothing's assumption free, okay? But you are literally having the most influence by having those assumptions in your model, okay? And assumptions are only as good as like how much you think about them, right? And so like we should be using expert opinion to build our models, okay? And Bayes' theorem provides us an extra way to do that, okay? Now Bayes' theorem also provides us a way to quantify uncertainty. Okay, and so again, if you're in situations where you're doing like machine learning, for example, the next big thing is going to be Bayesian machine learning, I think. Okay, and it has a lot of uncertainty quantification with it. Okay, and so this is just one small example where I had roughly 40 minutes to convince you that Bayesian stats is a cool tool that may help you in research. And again, it may help you in the opposite direction of big data. Like if you have small data sets and you have a lot of expert knowledge, like it's a solid place to start.
Well, now we're going to talk about Markov chain Monte Carlo, and then Josefina is going to talk about how to check this algorithm. So basically, this is the most used algorithm nowadays to fit Bayesian models. And the idea here is to split this name into what is Monte Carlo first, and then see, well, Trevor already mentioned something about that, what the Markov part is adding to the Monte Carlo. So first, what does Monte Carlo mean? And this is basically just an algorithm from which we can obtain random samples. And those samples are independent. And one of the characteristics of this is that we are sampling from a distribution that we know. And that is important because then we are going to see what happens if we don't know that distribution. So basically, this Monte Carlo is in some way similar to bootstrapping, because in bootstrapping we know our data and we sample from that data with replacement. And in this case, we know the distribution and we are sampling from that distribution. But this is basically something that is not related to the data itself, but it's something related to computational implementation of the algorithm. So for what we can use this algorithm, basically, once we have those Monte Carlo samples, we can use those samples, those Monte Carlo samples, to approximate integrals. And that's something that you can see in literature as Monte Carlo integration. So basically, we can use those samples to approximate integrals. And we can also, with those integrals, we can approximate the probability distribution itself, or moments of the distribution. And something that Trevor was already talking about, and probably is one of the most powerful benefits of this algorithm, that is, we can approximate even moments of functions of random variables. That those functions of random variables are called derived quantities. So just to see how this Monte Carlo works, I'm going to use a quick example just to see another type of data. And for this example, we are going to assume that we have a field planted with corn, and that corn might be affected by a disease. And we want to know for that field, which is the probability of finding a diseased plant. So our response variable, we are going to sample plants, and we are going to see if that plant is diseased or healthy. So basically, we are going to have zeros and ones. That's going to be our response variable. But we are interested in the total amount of plants that we are going to be sampling. So assume that we sample 50 plants, and 30 out of those plants are diseased. So we are interested let's say, in the sum of ones in our sample. So if we our y response, or the response variable, is going to take a value equal to 30 in this example. If we add some assumptions, as Trevor was mentioning, and if we assume that the location of the plants, the health of the plants is the location, something that we can discuss then. But if we assume that the health of the plant is independent of each other, and the probability of a given plant being diseased is constant, then we can assume, or we can say, that our response variable follows a binomial distribution, where n is equal to 50, and the probability of success of a diseased plant is p. But the point here is that we don't know what p is, but what we do know, because of literature or expert knowledge, is that p has an expected value equal to 0.3, with a standard deviation equal to 0.1. So based on this information here, we can decide a distribution, and based on those values, we can define the parameters for a distribution. So we can basically define a distribution for p that we are going to call prior distribution, that it's a representation of not only our prior knowledge, but also our uncertainty on p before we collect the samples. So once we have the binomial distribution for our response, that is basically the likelihood function, and after defining the priors, we have all the elements that we need to write our Bayesian model in this case. Basically, we can represent, as Trevor showed before, we can represent the posterior distribution of our parameter p after observing the data. It's going to be the product between the likelihood and the prior. It's just the product between the probability mass function of this binomial distribution times the probability density function of the beta distribution. And you can work with the math here. We are not going to do that. But basically, if you multiply, you can believe me, not me, but the literature. If you multiply those two distributions, you're going to end up with also a beta distribution. So we know that our posterior distribution for this parameter p, it's going to be also a beta distribution. But what we can see here is that this new beta is, oh, sorry, I forgot to say that the prior that we selected for this p parameter is a beta distribution because it's basically a probability that can take values between 0 and 1. So now what you can see is that this, although we have a beta distribution, these parameters, these alpha and beta, are updated based on the information that we collected in our samples. So our new alpha that was 6 before now is y plus this alpha that we had before. This y is this value here. And then the beta now is equal to n minus y plus beta. So basically we are combining our previous belief that we had, that belief or knowledge in these two parameters with the information that we collected in the sample, in the field now. What you can see here is that the prior and the posterior is the same form, right? Those are two beta distributions. And that is a special case in Bayesian statistics that is called conjugate distributions. When you have a posterior that has the same form than the prior, those distributions are called conjugates, and we say that the beta distribution is a conjugate of the binomial distribution of the likelihood. In this case, the beta binomial model, that is this model in particular, is an example of conjugate distributions. So now we are going to see how we can, I'm going to keep this, how we can use Monte Carlo sampling to come up with our posterior distribution. So we know, since we can solve this using, as they say, like pencil and paper, we know which is our posterior distribution. So basically, the only thing that we have to do is combine our prior knowledge with our data that we collected in the field. So we know that n was equal to 50 and y equal to 30. The only thing that we have to do is doing this simple math here and plug these values, these our alpha nu and beta nu, in the beta distribution, and we sample from that new beta distribution that is our posterior. So this in R, you can use this R beta distribution to sample from that. We took 1,000 values from that posterior distribution, and we come up with this posterior distribution here. So this was our prior, and this is our posterior after updating that prior belief using our data. I can tell you because I know which was the value of P in the data, and the value of P in the data was 0.6. So we can see that now that value was kind of here, but since our prior belief was, or our prior knowledge was like more into the left of this graph, now the posterior is kind of a combination of those two knowledge. So once we have that, once we sample from that posterior distribution, for that green distribution, we can use Monte Carlo integration to come up with, or to summarize, as Trevor said before, to get different summaries of this distribution. So in R, we are going to use the mean function to get the expected value of that distribution, or to approximate the expected value of the distribution, that in our case is the distribution of the p parameter. The bar function to estimate the second central moment of the distribution, that is basically the variance. And then the quantile functions to, or function to come up with a credible interval for that p parameter. So this is basically Monte Carlo in action, let's say. And now we are going to see why we need like the Markov part in Bayesian models. And the reason behind this is that nowadays the models that we use are more sophisticated models. We have more parameters, or the mathematical or the deterministic models is more complex than we are seeing here. And the problem with that is that as we have more parameters and we have more complex probability distributions, it's most of the times impossible to integrate the joint distribution or to integrate that posterior distribution. And there is where the MCMC helps us, because this algorithm helps us to approximate integrals, but without using formal integration. So basically, we can use this to get the marginal posterior distributions of the model parameters without involve formal integration in our estimation. So Trevor already mentioned this. Basically, what the Markov part is doing is also the MCMC is also an stochastic method to sample from a distribution. But in this case, it's Markov, the algorithm, because now we don't have independent samples, but we have dependent samples. So in each step of the algorithm, or in each iteration, that value depends only on the previous value on the iteration. I think we can, I don't have here an algorithm working, but we can see it in the example that Trevor had in his presentation. So one of the differences also between this, or what we are doing when we apply Markov chain Monte Carlo, is that we can sample, there is no need to know the probability from which we are sampled from. But what we have to know is something that is proportional to that distribution. And in this case, for example, this a Bayesian model 2, you can see that here I put it the proportional symbol. This is something proportional. This is not the closed form of the distribution. But as far as we know this, we can move forward with the MCMC algorithm. So there is no need to know the closed form of the distribution from which we are sampled. So there are different MCMC-based sampling techniques, but the most general one is known as metropolis hasting. And in that algorithm, we have a proposal distribution that is just a probability distribution from which we take samples and propose or values, and propose those values as potential values for our unknown parameters in the algorithm. And so then those proposals or those proposed values are evaluated, and those values can be either accepted or rejected based on an acceptance probability. And well, if we accept that value, the chain moves forward, and if we reject that value, the chain is going to remain in the same stage in the next iteration. Based on that proposal distribution, this general way of the MCMC can take different names. And probably Josefina knows more about this, but these algorithms has different efficiency, let's say, computationally. But in this kind of sample that is called random walk sampler, our proposal distribution is a symmetric distribution. So it's like the probability of a given value is equal in either sides of the expected value, let's say, of the distribution. Then if instead of fixing the proposal distribution, we update that proposal distribution in each iteration. In this case, it's using something that is called Hamiltonian dynamics. We come up with this Hamiltonian Monte Carlo algorithm. And these are not the only three, but these are probably the most known ones. There is one that is called Gibbs sampler or Gibbs updates, that in this case the proposal distribution is already the posterior distribution. So in those cases, we are not rejecting values because we are sampling already from the posterior. So there we accept all the values with probability 1. So these 3 examples show us that we can have 2 types of cases when we sample from the posterior distribution. One of them is called rejection sampling or accept rejecting samples. That is the first 2 cases that we proposed a value from a proposal distribution. That value is accepted or rejected based on or depending on how well those values fit into the prior and the likelihood. And the other case is this gives sampling updates. That is when we sample already from the posterior distribution. So we keep all the values. We are not rejecting the values in that case. I think you mentioned about the programs that we can use because I think it's true that it's easy to program the MCMC by hand, but sometimes the models become more complicated and it's more complicated to program by hand too. So we can use different open softwares to help us to build the MCMC algorithm. These are the 3 most used ones. The JARX probably is the most famous because I think it's the oldest one. You can use JARX in R via RJAX. That's the package that you can use there to run that language. This package uses a general way of metropolis casing or Gibbs sampler, depending. Even the name is just another Gibbs sampler. Understand is probably becoming more important now, and it's probably nowadays the package or the software where you can find the most or the highest amount of resources or the support. It has a huge community, an active community, and you can use this. Well, this package uses or this software uses this algorithm, uses Hamiltonian Monte Carlo, and you can use this also in R. There are different packages in R to do it. You can use this also in Python and Julia and other softwares too. And the last one that is one of the most famous ones is Nimble. In R, the package has the same name. And this package uses language similar to JAX, but you can also use you can get the posterior distribution or approximate that distribution using sequential Monte Carlo. That is not an MCMC-based algorithm because there are other algorithms beyond the MCMC ones, like Laplace approximation. You can also use that to approximate your posterior distribution. So basically, just to make a summary. No, this is just an example. In this case, I mean, if you want to do this with real data, you probably have to look for which are the values of these parameters. And as far as I remember from plant pathology, if you get the incidence of the disease, it's something similar to this. It's with which frequency, let's say, you can find a diseased plant. So let's say that you know that the incidence is 0.3, and you collect different papers in the literature, and one paper says it's 0.3, the other says it's 0.5, the other 0.1, whatever, you are going to get also a standard deviation. And with this information, you can use probably method of moment estimations to know which are these values here.
So here is alpha is intercept, or?
No, these are the 2 parameters that makes this beta distribution to take a certain shape. Or in this case, these 2 parameters, because when you have a distribution, you have parameters that are like, or giving that to that data the shape of the distribution. And these 2 parameters are giving this distribution a given shape where you can have this expected value and this standard deviation. If you change these numbers are going to change too. Just to summarize this, we use this algorithm to fit the model to the data. That doesn't mean that we are going to check those assumptions using the output of this algorithm. And that's what Josefina is going to talk now.
My favorite part about using JAGS or STAN, because I did my PhD in agronomy, and most of us have all these ideas in our minds of how our systems work, but it's really hard to find likelihood-based software that can actually put all these ideas into a single model. And then if you code in STAN or JAGS or Nimble, you have to learn how to write that language. But once that's done, it's basically just writing out your statistical model, which is actually a great practice because you have to be very explicit and you have to define each part of the model, which is very easy to forget if you use NLME or LME4, which are great packages, but are very automatized, and then you forget a lot about a lot of assumptions you're making. So if you want to get creative, you can spend a lot of hours coding your own MCMC from scratch, but if you're on a very tight time frame, you might just try out JAGS or STAN or Nimble. And the thing is, these softwares usually assume, like all the inference and all the predictions we make are basically assuming that the MCMC part of our model fitting went well. But we have to, especially when we use software like JAGS, STAN, or Nimble, there's a lot of things we have to check. That's why in the model diagnostics part here, it's divided in computational diagnostics and then model checking and actual model diagnostics. Because first of all, we got to check that the MCMC part went well. And I think this is going to improve with time. But right now, there's a few things we really have to check and kind of babysit in traditional MCMC software. And it basically boils down to, is the sampler mixing well, and has it reached the what we call the stationary distribution, which means that it reached like a stable mixing part, and it's actually sampling from our target distribution, which is what Francisco showed previously. So there's like only a few problems we can solve with pencil and paper. Then there's a few more we can solve probably coding from scratch. But then once you get creative, you use these softwares, and that's the thing you want to check. And so you can check conversions either visually or with some metrics that tell you if it converges or not, which would be R hot, for example, from Gelman. And then visually, it's very easy. And I saw someone with the Statistical Rethinking book, I think, yeah. And Richard McElrath actually calls these, when the chains are mixing like this, he calls them, I think, happy caterpillars or something like that. Like they have to look nice. They have to look very well mixed. And this would be an example of happy, or at least you would be happy if you get a trace plot like this. It's basically showing the value for whatever parameter you're estimating with your model versus the iteration number. So they are correlated because it's Markov, but they're basically mixing well and sampling from that stationary distribution. Whereas in this case, it's the same thing, but this is sad because it's not mixing well. You see that you have two chains which are basically independent Markov MCMC algorithms that started at different points. And so these are actually not mixing at all. Something went wrong, and this can be either you need more iterations, your model is probably kind of funky or very different to your data, and you probably need to re-specify your model. We could be talking about this for months. Like, there's a ton of things here to check and possible things that can go wrong or not. But this is more to give you guys an idea of, like, first check that all the computational part went well before checking your model. And then there's stuff like effective sample size, which also goes back to is the chain mixing well. And then there are very software-specific metrics that you might want to check. But they are usually these softwares have guides for users, which are Stance. I really like Stance. It's very well documented. So you can go there. It also has a very good active community. So that's usually the place you want to go and see what things there are out there to check. And then ideally, before fitting your model, you would go and simulate data. So like, it could be plant density, yield response to plant density. So you would fit in corn a model that goes like y is beta naught, beta 1, x, beta 2, x squared, something like that. You would generate data from this model, and then you would fit your Bayesian model to that data. And if it gives you back the true parameters that you basically decided arbitrarily, then it means that the model is actually doing what you think it's doing. This gets way more complicated, especially when you have latent variables, which are variables that are a level deep compared to this. But it's always a good practice, and it allows you to troubleshoot your models much better. And since we're talking about the different guides from the different software, it's just a message just to be a little bit suspicious about the software that don't have very good documentation, because this is a part that you really want to make sure works before you make inference and prediction, right? That's why I put that out there. Checking and improvement is another topic we could talk about for many days. We have 5 minutes. So I put it out in basic steps. We could probably make this way longer, but first of all, as I guess you do for any analysis, is checking if your inference, so if your parameters actually make sense, if that's something you can, from previous work. So if, for example, in Francisco's example, if the theta parameter was between 0 and 100, if it wasn't, that means something's probably off. And then I put this example. This is not really model checking, but I put it out here because I sometimes get these questions when I'm consulting. And it's basically, why is not my posterior just like my prior? So you could get, in these plots, I'm showing histograms of theta, or theta giving the data. So the posterior, theta would be just the prior. And sometimes people get exactly the same thing. And that's usually, I mean, it's not wrong, but it's probably telling you that your data didn't contain enough information to shift your posterior away, right? So, so the posterior is the yellow histogram, and the prior is the blue histogram. Then when you actually get some type of shift, you can say, okay, I learned after looking at my data, and this is my new belief. But yeah, that would be the part of the inference. And then a big part of model checking is posterior predictive checking, which is in all these books, and I also added the BDA3. But parameter unidentifiability would also present itself in other ways. This is not the only way it could present itself. But yeah. Where was I? OK. So posterior predictive checking is basically checking if your model airplane or model boat is resembling the boat you're observing. I mean, maybe I won't do this analogy. Basically, is your model, your posteriors are producing data that look like the data, are distributed like the data you observe. So basically, we don't want more extreme values than we actually observed, and we don't want just like a very narrow range of predictions. So we want something that looks, again, histograms of the data we observed and the data we predicted. The data we predicted is the yellow histograms. So in this case, it basically resembles the distribution. The posterior predictive distributions is similar to the distribution of the data, which is what we want to get. And here we have like a very narrow range of predictions, which is, again, probably something's off in our model. We're not taking something into consideration. There's also like a thing called Bayesian p-values that actually compares your model to your predictions. And do you have any guess of what type of p-value you would want to have? Like greater than 0.05, lower? You actually want a Bayesian p-value of 0.5, like right in the middle, because that means your model is not generating data that are more extreme than your observations. That's all this part is about, checking that your observations match with your model or with what you fit. OK, we're going to go kind of fast, but you can stop me at any point. The last part I want to talk about is model improvement. Andrew Gelman, the author of this, one of the authors of this book, talks about this a lot. And it's basically reiterating over a same model can give you a lot of, can make you understand a lot of your system and a lot of how your data is generated. So, and in this part, you usually, Trevor showed this a little bit, but you can fit a model with very few prior information or a model with a lot of prior information and see how your inference changes. And you learn a lot by doing that. The practice of reiterating over the same model or some parts that change allows you to understand a lot about that. And then you usually want to go fit one model, fit a better model, a little bit better. And then there's a point where you will actually create worse models. But that's good because that actually lets you know that the model you had before was actually better and you should probably stop trying. It does take a decent amount of time, but we also, most of us, I think, work on problems that allow us to take our time to fit the model, think of the problem. There's no need to fit a model in like 10 minutes. Just for the sake of time, I'm going to let you guys read these. It's very similar. I mean, some of these, well, we have predictive performance metrics. In the case we want to know how our model does in terms of predictive performance. Some of these are usually trying to see how our model would do predicting out of sample data, but do that with the data they actually use to estimate the parameter. So it's kind of using the data twice. That's why we usually use cross-validation. There are some computational tricks, like this leave one out by Vitari. These computational tricks actually use the expected log predictive posterior density to find out what the leave one out cross-validation would be. To compare, this is all to compare models and see if you're improving or reducing the quality of your model. Important parts is in cross-validation, then if you have the time to do your own cross-validation and leave 1 year out, 1 farm out, or whatever, always respecting the structure of your data, that's great, and that allows you to learn a lot about your model, where it's performing very well, and when it's not. Because we're also not gonna fit a model, or probably not gonna come out with a model that does everything perfect. All models are wrong. But it's great to learn and see which ones can do the tasks we want and be aware of the things they are challenged at. So that's something to keep in mind. And especially if you're reviewing you might not fit Bayesian models yourself in the next year, but you probably will get, because as we saw in the introduction, Bayesian models applications are increasing. And you might get review requests for a paper that applies a Bayesian model. I recommend to look at this table 1 in this paper. Check it out. And it basically contains some information that people should report in order to say, okay, I fit my Bayesian model, it's working. You can trust me in my results. And to finish up, and then here more useful references, cool books, some cool papers. Just to wrap up, some things we learned. Bayesian models are good. We're basically making more assumptions, but we are getting a lot more inference. We can solve a lot of problems, especially in agriculture. It's a field that has a lot of small data problems, a lot. So I think if we apply it responsively, it's a great tool. And also, I like this, like the typical phrase of we're standing on the shoulders of giants. We have a lot of information to specify our priors. Like Francisco did if you look at his paper, he did an insane literature review that contained a lot of information to inform those priors. So that's a lot of advantage we can take. And just, this is all enabled thanks to the new MCMC algorithms. And last but not least, don't forget to check, because that's what's allowing us to make all these inferences and predictions. It all has to, the MCMC algorithm has to be working, and then typical model checking tools, especially since we're making a lot of assumptions, have to be there. And with that, thank you.